So, hello everyone. Good morning, good afternoon, good evening, good night to wherever you are. And I hope that a lot of people can join to our first of two sessions on artificial intelligence and machine learning of this year's ESEM conference. We have three technical papers in this session. Just a reminder to the authors, we have 10 minutes presentation plus 5 minutes of questions. If I feel that you are running out of time, I will just step in and be visible just to remind you that you should finish your talk. If any one of you out there want to ask questions, please make sure to leave a comment in YouTube or Facebook video screens, and we will ask the questions afterwards. So, and without much further ado, I'll just hand over to the first paper and introduce to you Yuekai Huang, who will present their paper on the quest for the golden approach, an experimental evaluation of duplicate crowd testing reports detection.
Hello everyone, my name is Yuekai Huang. I'm from Institute of Software Chinese Academic of Science. Today I will present our work, Quest for the Golden Approach, an experimental evaluation of report detection. The background of our testing, which uses crowdsourcing for software testing. Unlike outsourcing, crowdsourcing workers can come from anywhere else, and the cost of crowdsourcing is output-based. Therefore, using crowdsourcing for software testing can bring together workers different testing requirements, background, and skill sets to obtain a more reliable, cost-effective, and results. And this is typical crowd. Firstly, the task request distribute the task list and the software under test online. Then the crowd worker accept tasks and reports. The task request receive reports and discover bugs through distribute the crowd testing process. The crowd worker may many reports, but due to the unpredictability of this process, workers may submit the same bug, which lead to duplicate. Although many approaches have to automatically detect the duplicate, the comparison among them and the practical guideline approach in crowd testing remain weak. So we want to explore the approach for crowd testing reports. More concretely, we want to provide a new insights and guidelines to select the appropriate duplicate crowd testing report detection. To achieve this goal, investigate the existing approach first, then use this approach to on the crowd testing data set. And some indicators such as used to compare each approach to obtain the guidance for the selection of the detection approach in crowd testing scenarios. And for the literature review, we database DBLP actually explore and the ESEM digital library a source of use the following search terms for retrieval. And we know that duplicate sentences detection will be utilized for duplicate crowd testing report detection. So we set the search terms with text or sentence to include these studies for exploration of existing approaches. Among the numerous retrieval records, we only focus on 4 peer-reviewed sentences detection papers with result and detailed method description. Discuss the papers unrelated to duplicate detection and theoretical research about duplicate detection and refer to duplicate detection approaches. And we filter the papers by the title, abstract, and the full text. And in the end, we performed a quality assessment and got at least 10 papers. Utilize techniques. We group into 3 categories. The first category contains 2 approaches. They applied techniques for duplicate detection by computing the similarity to reports. The second category contains 3 approaches. They design a set of report similarity from various aspects and to determine whether two reports are duplicate. The third category contains 5 approaches. The main idea of learning is take a similarity to of reports with technique for duplicate detection. The literature review, we put forward 3 research questions. One is which approach is more effective for crowd-testing report duplicate detection. The second is, are these approaches sensitive to the size of training data? The third is what is the time duplicate detection approach? And to answer these 3 questions, we collected 414 crowd-testing projects from Baidu crowd-testing platform. And as some approaches are originally designed for the duplicate sentences detection, in order to provide a more thorough view of the performance of the 10 examining approaches, we also employ the Stanford Neutral Language Interface dataset to conduct sentences matching experiments. Answer research question 1. For the 400 crowd-testing projects, we use 300 projects for training. We use the left 114 projects for testing. Use the performance of the 10 duplicate detection approach. We also conduct a man-Whitney test pair of these approaches and rank them based on their performance and whether the performance difference is significant. Specifically, we start from the approach with the highest performance and put this approach with which no significant performance is observed into the same ranking bucket. And then iterate the process on the remaining approaches. Not the approaches in the ICE ranking. We can easily see that the machine learning based approaches, MIP and DL, BM, PM are ranked in the first and the second level in most evaluation, which means they are the best 2 duplicate detection approaches. And to back the performance of these duplicate detection approaches, we also run them in duplicate sentences. We can see the top 4 ranked approaches on the duplicate sentence dataset are based approach. It's quite different from the performance on crowd testing, which 3 of them is ranked almost in the rear of all approaches. This shows that the deep learning based approach might duplicate crowd testing report detection, and this might be due to the local bias issue proposed by Wang et al. In the crowd testing report classification task. Specifically, the report different domains of testing application will use quite different terms. For example, navigation and location in lyric song in music domain. When we conducting a duplicate detection in testing projects with emerging term in new domains, some approaches might fail to. In addition, we found in crowd testing dataset and duplicate sentence dataset, DL, ML, STM, and DL, CNN are worse than the DL, DCN. Reasons and find that the basic network structure of the first 2 approaches is different from that of the last 2 approaches. And DL, DCN will first encode the single report, then use the interactive representation of the 2 encoded reports for further feature extraction and similarity prediction. And on the contrary, DL and ML only encode a single report for similarity computation. Hence, DL, ML, STM, and DL, CNN lose the interactive information of pair of reports. And to answer the question 2, we experiment with different numbers of projects as training data set while keeping using the 140 testing data set. This figure shows the performance of, and the table shows the ranking. We can easily see that most deeper learning-based approaches are sensitive to the training data set, and MIP is the best approach for small data set, and MIP and DLBMPM have high performance in large data sets. And to answer research question 3, we record the time to run these experiments, and we evaluate the performance of this the build model on an average size crowd-testing project. We can see learning-based approach employing the are more time-consuming than others. This may because they are needed to the time sequence, which makes training more complicated and time-consuming. And nevertheless, build step can be conducted offline. We duplicate detection time, and even with the most time-consuming approach, BRMPM can be done within for a typical project. For other less time-consuming approach, like duplicate detection can be done within 1 minute. Last, let me make a conclusion for our work. In this work, we conducted the first empirical evaluation of duplicate detection approaches in crowd-testing report, and we found that MIP and DR the best two approaches for crowd-testing duplicate detection were to the data size. We also found that the several deep learning-based approaches might fail in duplicate crowd-testing report detection due to the local bias issue. And for the deep learning-based approach, interactive information can improve the performance of duplicate crowd-testing report detection. And that's the end of for your listening.
Okay, Yuekai. Thank you for your presentation and for being on time. We have, I think, 2 questions from the audience. One is, Yuekai, do you think, or how would you organize employees considering both machine learning and traditional manual repeat selection methods?
Yeah, it's a good question, because for the manual data selection is hard work, usually time-consuming and effort-consuming. And if we have a high-performance duplicate detection approach, we can predict the probability of the report, and the worker can focus more on the high scored or low scored report and trim the high scored as duplicate. And also they can the workers also previous reports, and otherwise he can determine whether the current report is duplicate or not. So the duplicate detection approach has a high performance. We can list the similar reports and release workers from numbers of reports.
Okay, I think you had some gaps in your voice. So, but thank you for your answer. Second question is, if you use another data set, how sensible are your approaches or the approaches that you tested to the data set? What do you think?
But for our experiment, we created the largest, one of the largest crowd testing, and have different data project size. So our data set, I think, is suitable for our experiment. And if you use another data set, Mike can, I don't know, maybe we can consider that in the future work, investigate in the future.
Okay, Thank you very much. And with that, thank you again. And we'll go to the next presentation because we're running out of time otherwise. Aravind Nair will present funcGNN, the graphical neural network approach to program similarity. Aravind, stage is yours.
Yeah. Can everyone see my screen? Hello.
Not yet. Wait a moment. It should be already visible. I think that's.
It's not coming.
Probably have some technical issues. Now.
Yeah, now it's there.
Perfect.
Okay. So yeah, hi everyone. Good afternoon. My name is Aravind Nair, and I'm a doctorate student at KTH Royal Institute of Technology, Sweden. Today we'll discuss our paper funcGNN, a graph neural network approach to program similarity. I can't move the slides actually. Yeah. So this paper was co-authored by Karl Meinke and Avijit Roy, who are employed at the Theoretical Computer Science Department at KTH. And this entire project was funded by Testomat, which is an ITIA 3-level project, European project. This will be the agenda for today's talk, and we'll go through in this format. Finding similarity between any two objects is a crucial task for many computational tasks like recommendation system. One such area where similarity plays a crucial role is software engineering. Program similarity is one of the fundamental concepts central for many multiple software engineering tasks like software plagiarism, clone detection, code refactoring, and code search. Software similarity, basically the idea is to find out a similarity metric, how one program is structurally and semantically similar to each other. This is a very crucial and difficult task because a small change in the logic can make it look structurally similar but semantically different. According to the literature, one of the effective methods to analyze programs are by converting them into graphs. And one of the most commonly used approaches are the abstract syntax trees or the control flow graph CFGs. Thus, the idea of program similarity can be tackled by mapping this problem of similarity to a graph similarity problem. One graph similarity, though programs provide a good model for analyzing programs, analyzing or calculating graph similarity is an expensive task. One of the most commonly used graph similarity approach is the graph edit distance, or the GED. And it stands for the minimum number of operations required to transform from one graph to another. This is the same concept of edit distance algorithm like Damrow-Levenstein algorithms used for string matching in the natural language processing domain. This procedure of calculating GED is NP hard in nature, and it is very computationally expensive. Based on the research here, it has been proven that it is difficult to compute the similarity score between graphs of more than 60 nodes within reasonable time. Thus making this applicable to large software repositories or industrial application completely difficult. To solve this problem, first what we do is we convert a program to a graph structure called as control flow graphs. As you can see, this is the pseudocode of a program and its corresponding label control flow graph. It's basically a cyclic directed graph where each node represents an atomic statement in the program, and the edge represents the execution order, or the order in which all these statements will be executed. Control flow graph thus preserves the logic, structure, and semantics and can be used for analyzing programs. Once we have calculated the control flow graphs, or once we have labeled all the nodes in them, the next task is to process them using a graph neural network. A graph neural network is a deep learning based graph architecture where each node and the edge is given a unique embedding or one hot embedding based on its label nodes. And in the training phase, all these nodes pass their embeddings to each other using a message passing algorithm and update their embeddings. And this is how the overall neural network learns to provide an entire embedding for the graph. Now we'll go through the architecture of a paper funcGNN. Suppose we have two programs, PA and PJ, and our task is to identify their similarity. We do so first by converting them into their control flow graphs and label each node accordingly. Each label nodes are given an one hot embedding representation, which relates to their nodes in the graph, and it is passed through a graph neural network called graph sage. The role of this graph sage is to update these one hot embeddings and create a final node embedding for each node in this graph. Once we have achieved these node embeddings, the next task is to compute the overall embedding for this entire program or entire graph. And to do so, we use an attention mechanism. The role of the attention mechanism is to give more weightage to structurally and semantically significant nodes in the program. Once we identify the two embeddings for each program accordingly, now the task is to identify their similarity. We do so by two approaches, and the first one is a top-down comparison. In the top-down comparison, we use a neural tensor network, that is this model here, and we compare the overall graph embeddings of both the programs. The second approach is a bottom-up approach. Here, instead of calculating the similarity of the entire embedding, we calculate the similarity of the atomic nodes in the program and create a using a histogram feature set. We identify their similarity function. These two similarity measures are then concatenated together and pass through multiple fully connected deep neural networks to identify to estimate the final similarity score of the two programs. For our experiments, we used 225 Java unit functions and created a program pair set of 50,625 program pairs. We used an 80:20 split ratio where we use 80% for training and 20% for testing. The average graph size is for our dataset is 19, which is way more than the literature survey, which showed that it is impossible for or difficult for more than 16 programs. As I mentioned earlier in the initial slides that calculating graph edit distance is a computationally expensive task, identifying the ground truth was a serious problem. To solve this, we used an approximation method called as QAP, or the quadratic assignment problem, to identify the or to estimate the approximate graph edit distance or approximate similarity for all the program pairs. Here are the distributions for both the test and the training dataset. To evaluate our model funcGNN, we use two metrics, the mean square error and the total time taken for all the experiments. We compared our model funcGNN with traditional graph approaches as well as the other graph neural networks. The mean square error is basically the loss or the difference between the predicted score and the actual ground truth. Since we use the quadratic assignment problem as the ground truth or the base method, the error obtained there is kept 0. And as we see from this table, our prescribed or our proposed model achieves the least amount of mean square error, thus making it really state-of-the-art algorithm. The next metric is the total time taken, and by total time taken we mean the amount of time taken to estimate the graph similarity of all program pairs in the dataset. As we can see from this table as well, the graph neural network approaches can take considerably low amount of time than the traditional graph approaches. To understand our model better, we took 3 case studies where we evaluated the model performance based on programs having high similarity, low similarity, and we took an example where the programs had an high error rate. As we can see, the amount of error between the prediction and the ground truth is really small, which suggests that the model is really good for calculating or estimating the similarity measures between 2 programs. To summarize our work, we propose funcGNN, a graph neural model for program similarity. In our approach, we use the graph edit distance as the similarity matrix, and to our knowledge, this is the first time a graph neural network has been applied on label control flow graphs of high-level programs like Java. The graph embeddings produced or generated by the funcGNN model are inductive in nature. That is, it can generalize to unseen nodes or programs in the dataset. And it is a learnable model as well. And by learnable, I mean if we substitute graph edit distance with any other similarity metric, it can easily learn just based on the weight approximations or weight corrections. The metrics and the results obtained by our model shows that it really achieves low error rate, and it is faster and scalable than the other graph approaches. In the future work, we plan to analyze or increase the size of our programs by analyzing more than unit functions. And we also in our work we currently we did for Java unit functions, so we will like to give support to other languages such as C and C++. We also plan to apply our model on large industrial repositories for tasks like clone refactoring, clone identification, and software plagiarism. Thank you for listening to it talk, and if you have any more queries or any for more information, please use the following details. Thank you. Hello. Yeah, I can't hear actually. Maybe we can
That's
go.
true, sorry. Now
Yeah.
you can hear me? Okay. So thank you for your presentation. Thank you for staying on time. We have a few questions, and one is a question that I also had is, what is the difference between what you did and clone detection, or rather, how does it compare in the results? Can you elaborate on this?
Yeah, sure. The difference is not that much actually. Clone detection, the idea is you find between the entire program, and right now one of the limitations or the scope of our project was just to find the similarity between unit functions or unit Java functions. In clone detection, we generally go for the entire program or for the entire class file, and also it will be multiple unit functions and a class file and all those things. So clone detection will become as a next version or the higher version of our work which we are planning to tackle in our future work.
Okay, thank you. Second question, I think it's a similar one. One part of the question is, does each node represent one method? And I think you said it's one statement, right?
Yeah, so I'll just answer that and then we can go for the next question. So each node in the control flow graphs represent an atomic statement in the code. Like it can be variable assignment, or it can be a mathematical operation, or it can be a loop assignment or anything. And for each that operation, we the graph neural network or our prescribed model identifies a unique embedding which is the best way to represent that atomic statement. So it's basically like that.
So the interesting, sorry.
Yeah, and then how we do is once we identify the embedding for each nodes in the graph, the next task is to identify the overall graph embedding by summarizing all the node embeddings in that graph. And that is how we finally represent a graph, a program to a graph and graph to an embedding. And then once we get the entire finalized embedding, then it is like finding it's like vector similarity, finding the similarity using any two vectors.
So do you think, and this is the second part of that question, that is close to semantics or function of a method? Does it approach that?
So right now this approach, it takes more of the structural similarity and a bit of the semantic similarity, but we are also planning to do some architecture changes and get more abstract of the current labels to make it to understand the semantics in a much more better way.
Okay, thank you again very much. Now we go to the final presentation of this session already. Time is really fast. This will be Juri Rocco, who presents TopFilter, an approach to recommend relevant GitHub topics. Juri,
Okay.
have fun. Good luck.
Thank you. Thank you for your introduction. I'm Yuri, and I'm presenting a paper titled as TopFilter, an approach to recommend relevant GitHub topics. So, TopFilter is a collaborative filtering approach to recommend GitHub topics. By considering GitHub topics as product to recommend, we improve repository popularity by suggesting a list of relevant topics. So, GitHub is nowadays among the most popular platform to handle and maintain OSS projects. In this page, we can see that recently GitHub reached more than 100 million of repository and then more than 40 million of users. Given this number, it is obviously that they should provide mechanisms to improve the reachability and searchability of a repository. Okay. To deal with this issue, GitHub recently introduced the possibility to tag repository employing topics. Topics are terms used to characterize repository and to facilitate their discoverability. From software developers who are searching for existing projects, providing them with some reusable features. In particular, we can see that currently GitHub counts more than 700,000 on topics, and only 180 of them are identified as a feature topic. In this slide, the left picture suggests the usage of topics for the user to improve the reachability of the repository, while the right picture depicts an exception of feature topic identified by the GitHub organization. There are two existing words, in particular repo topics and multi-naive Bayesian network, that mine the information in the textual content in order to suggest relevant topics. The first one mines both README files and textual content, and the second one mines all the README files to recommend just the featured topic, the ones that have been identified by GitHub organization. Okay, by this simple snapshot, a GitHub user can figure out that the spaceship generator repository make use of Blender script for procedural generation of 3D spaceship. In particular, there are 6 topics. 2 of them are featured topics like Python and 3D. And in this particular case, game development is not nor a featured topic, and also it is not included in text context. And for this reason, game development can be never recommended from the previous work. Okay, just to have the test of the collaborative filtering technique calculates the missing rating by taking into account a set of items rated by similar customer. So collaborative filtering techniques have been conceived in the converse domain to recommend products based on the assumption that if users agree about the quality of or relevance of some items, then they will likely agree about other times. TopFilter works following the same line of reasoning to mine GitHub topics. If projects have some tags in common, then they will probably contain other tags relevance. In the picture, we will see 2 cyclists, both like pastime pizza, and the second one likes Coke. So Coke, it is a possible item to be recommended to the first cyclist. Okay, this is the overview of our approach, where the repository contributors are asking for a recommended topic by giving as input a list of initial topics. So this recommendation came from a GitHub project that has been parsed and encoded in a suitable way, and then this encoding allow to calculate the similarity between 2 repositories and then to recommend important and relevant topics. Now I'm going to detail each step of the approach. So the data encoder encodes the mutual relationship among GitHub repository in a project topic matrix. The first, in particular, in the bottom part of this slide, there are an example. So where for project contains a list of topics, in particular 6 topics. And the first step is try to reduce the number of topics by applying some NLP steps. In this particular algorithm and algorithms are combined in one tab, so algorithm, in order to reduce the number of topics. And then these information are encoded in a project topics matrix where each row represents the repository and the information about when the topics is included or not. When we have this representation, we can encode also this as a graph in order to enable the computation of the computation of the similarity. In particular, 2 nodes in a graph are considered to be similar if they share the same neighbor by considering their edges. In particular, we are using cosine similarity of the feature vectors. Then, given a project, the inclusion of the other topics is decided by considering the most similar projects. The rating for missing items is computed by means of rating from similar projects. So this formula is the one that we use in order to recommend relevant topics. So once we have defined the approach of TopFilter, we also use it in Untitled with the multi-naive Bayesian network that we presented in the first slides. So in particular, the multi-naive Bayesian network takes as input a list of README files and then compute the initial list of topics that has been given in input to TopFilter to give as output an augmented list of topics. So we evaluate our approach by using different metrics. So we assess the quality of the work employing a well-defined set of metrics commonly used in the recommendation system, such as success rate, accuracy, and catalog coverage. In particular, given the set of projects, catalog coverage is the number of recommended topics with the global number of the available one. This metric measures the suitability of the delivered topics considering all the possible set of values. And then we are trying to answer 2 different research questions. In the first one, we would like to know which TopFilter configuration has the best performance. We have different parameters such as the number of recommended topics, the number of top similar neighbor projects that TopFilter considers to predict suggested topic, and then the cutoff value of the initial topic that we will see in the next slide. And the second research question aims to check if the entitled usage of TopFilter with the multi-naive Bayesian network can be improved by means of TopFilter. So we use the same dataset employed to evaluate multi-naive Bayesian network, and we derived 5 datasets by using the cutoff. The cutoff, as you can see in the table, once the frequent topics have been removed, all the repos that contains less than the cutoff value topics are filtered out from the dataset, as they contain little information to enable the collaborative filtering prediction. So at the end, we have 5 datasets that change the number of topics and the number of the repository. We use this in our evaluation. In particular, this picture depicts how we evaluate our approach by having 3 phases: data preparation, recommendation, production, and outcome evaluation. The data preparation phase is conducted to collect the repository. The dataset is split into training and testing set. Due to the different nature of the recommendation system, testing and training set data needs to be specifically prepared for each approach. During the recommendation production phase, to enable the evaluation of TopFilter, we extracted a portion of topics from a given testing project, and we call it as a ground truth. The remaining part is used as a query to produce the recommendation. Since multi-naive Bayesian network uses only README file to predict a set of topics, it does not require any topics as input. Finally, the combined approach uses TopFilter and as the recommendation engine, which is fed by topics generated by the multi-naive Bayesian network. In this respect, both testing data and training set box are simplified to provide the needed data. Okay, and then the evaluation, the outcome is worth noting that we cannot directly compare TopFilter with multi-naive Bayesian networks since they rely on different input data. To be concrete, TopFilter is a supervised learning system that requires an initial set of assigned topics, while multi-naive Bayesian network is an unsupervised learning, and it uses only the information made from the README file. So this is the result of our evaluation to answer the research question 1. To find the configuration between the best prediction performance, we experiment by varying the available parameters, such as the number of recommended items and the top similar neighbor projects. The bar plot show the average success rate obtained by running the tenfold cross-validation technique with TopFilter. So TopFilter achieves a better performance when we consider a dataset with more topics for each project. This is understandable since TopFilter rely on availability of training data to function. So the more project it has, then the better it can compute the similarity among projects. To further to the TopFilter performance, we compute and depict in the scattered plot the precision recall curves for all considered datasets. For these settings, the number of recommended item n was varied from 1 to 20, to study the performance for a long recommendation list. Each dot in a curve corresponds to a precision recall obtained for each value of n. As a precision recall curves close to the upper right corner represent a better precision recall. The scatter plot demonstrated that by considering a dataset with more topics for each repository, TopFilter yields a better prediction performance. We investigate if TopFilter can recommend a wide range of topics to repositories by considering catalog coverage. The metrics, the table in the bottom of these slides report the catalog coverage values. We can see in the scattered plot the metrics mirrors the percentage of recommended topic in the training data that the model is able to suggest to a test set. And the higher value correspond to a better coverage. In the next slide, we can see the result to answer the research question 2, where we are trying to see how TopFilter improved the quality of multi-naive.
Juri, can you come to the last slide?
Yes, of course. So this is the last slide is just a conclusion. GitHub is one of the most platform to handle and maintain open source project. We presented TopFilter, a collaborative filtering-based recommended system to suggest GitHub topics. And then, considering multi-naive Bayesian network approach, we improve it by recommending an extended set of topics. We plan to extend TopFilter by adding different degree of similarity in function, and of course, to increase the dataset we used in the evaluation, and also considering other metrics like size, diversity, and novelty. So thank you for your attention. Sorry for being late, and then I'm here for some questions.
Thank you, Juri, for your presentation. One question that I have is, you have evaluated based on a data set. And
Yes.
do you plan to include, in this use case, authors of repositories at one point in time? Because I have found that if you use collaborative filtering, you have the problem with false positives. Let's say the biker in your example may not like Coke at all.
Yeah.
So,
so the question is, yes, of course, the lesson that we learn is that depending on the data set, the value and the quality of the performance can change. And for this reason, we are going to apply our approach on different data sets. So we started with the forms with the one that has been already used in another paper, and then in the next, as a future work, we are planning to add other dataset in order to see how the quality of the dataset impact on the prediction performance.
Okay. If anyone of the audience has a question, please just post a comment. Oh, no one. Yes. So what you said is you don't really plan to reach out to authors, right? So you look at different data sets and how they compare. So the recommendation could be to also look at what the authors say, because do I understand your use case, right? That it's, if I'm an author of a repository, your approach will suggest me to pick a good set of topics.
Yes.
Right? Okay.
Yes.
Which is very valuable if you think about people will be more likely to find.
Especially when we are in the first stage of the development, where we don't know how to classify or characterize our project, and it is important to see what happens in other repositories.
Mm-hmm. Because
we are relying on similarity about the project that we are developing to the project that is already developed, so we can take inspiration from these topics.
Okay. Thank you very much. With that, we have reached the end of the first AI and ML session in ESEM. We have now, I think, a 10 minutes break, and then we'll all be back for the second session, hopefully, on artificial intelligence and machine learning. It was nice to see you all, and have a good day.